So let us resume our discussion from the realization which we had in the previous class. That is, the quantum field which we are talking about is in fact a collection of oscillators in momentum space, and these operators or oscillators in momentum space together combine in a particular Fourier transformed manner to generate quantum fields in space time. Okay, so that is what we realized in the last class. We move forward in this class to see more clearly the oscillator structure and the quantization of oscillators as we used to know. The same machinery will be employed here, and we will get a bunch of oscillators with their quantum properties collectively making up for the properties of phi of xt. Before moving to that, let us see a previous thing which we had. Remember, the Hamiltonian which we had was a quadratic structure thing. There was a pi square which was like p square. There was a phi square which was a x square. But there was a gradient of phi square which normally we do not see in ordinary harmonic oscillator case. So therefore, we went to the Fourier basis where this gradient term became k square actually, which combined with this m square c square upon h square, giving rise to the frequency omega square. So that is the benefit of going to the Fourier space was. One thing I should make clear here, in this discussion we had traded delta 0 phi for momentum pi. That is a choice we chose. In fact, we could have chosen not to trade del 0 phi but to phi dot. There is this 1 over c difference between del 0 phi and phi dot. So del 0 phi is actually equal to phi dot upon c, because remember 0 means x0 means ct. So if I define my pi as a conjugate momentum with respect to phi dot, that means I try to trade phi dot rather than del 0 phi, then I will earn up an extra c factors here and there. For example, with respect to del 0 phi, there was no c here, but if I define my conjugate momenta by the legendary exchange of phi dot, I will end up getting an extra c factor. Therefore, pi phi dot, which we computed previously, we had taken pi del 0 phi. If I do pi phi dot, I will again end up getting an extra c factor as well from before compared to the previous case. So ultimately, what it does, if I stick to the definition of trading phi dot with pi, that is to say, define my Hamiltonian as phi dot pi minus L, while pi itself is defined as del L upon del phi dot, then what happens that this extra 1 over c square factor which I was getting uh, in the definition of the Hamiltonian exactly gets cancelled out, and I will get only pi square h4 plus gradient of phi square plus m square c square h bar square phi square. This is a useful exercise for you to try, and that is what we will proceed with. That I will not use del 0 phi anymore to do the legendary transform, but I will just use phi dot. They are just 1 by c apart, and therefore that simplifies the Hamiltonian because that is quadratic in either phi dot or in pi. So extra 1 over c square factor, which was appearing in the definition of Hamiltonian, can be reabsorbed in the new definitions of a pi. Okay, so that's what we will do. That simplifies just notational convenience. There is no conceptual point about it. So let us move ahead with this realization that now on my pi is the conjugate momenta, which is obtained by taking the derivative of the Lagrangian with respect to phi dot and not with respect to phi dot upon c. Okay, so again, as we discussed, I'm going to write down the quantum field phi xt, which is given over here, in terms of quantum fields in momentum space, which is given over here, and then take the Fourier transform. That means we combine them using e to the power I kx, where this k and this x are just real numbers, real vectors, not operators. Okay, so just to recapitulate the points we had learned, if I use this definition, ultimately I'm going to get oscillator kind of equations of motion for these variable phi k. For this variable phi, we did not get oscillator equation, remember. It used to satisfy Klein-Gordon equation. But the cost of the Klein-Gordon equation is the appearance of the Klein Gordon equation is replaced by a harmonic oscillator equation if I do get to the Fourier mode. Okay, particularly the gradient term is handled well in this thing. All right. So since this is a harmonic oscillator kind of a structure, I can again do the same kind of business which we used to do for harmonic oscillators. Namely, I can try to write down it in terms of ladder operators. If you remember quantization of harmonic oscillator, we used to write x as root under h upon 2m omega and a plus a dagger. You need to go to your quantum mechanics notes to just realize that this is how we used to write in terms of a and a dagger the variable x which satisfied the oscillator equations of motion. This was in Schrodinger picture where operators do not change in time but states change in time. If you want to know what was the Heisenberg picture thing, this was roughly similar to root under h upon 2m omega, very similar form. Only thing is that this will have e to the power minus I omega t and plus a dagger e to the power plus I omega t. So this is how the time dependent operator would have changed in Heisenberg picture, having a creation operator here, a dagger is a creation operator coming with e to the power plus I omega t, and an annihilation operator coming with a e to the power minus I omega t, where omega was the frequency the oscillator was satisfying. So similarly, I can have the same thing done for the phi k this time. It has its own frequency omega k square, so that omega k will sit here. It had its own mass which is 1, so this m will be replaced by 1, and everything else should be the same, only for one more fact that I have different oscillators for different k's. So frequency depends on k, so therefore this ladder operator a and a dagger should know about which variable has been written as oscillator, so they should also come with a label k, so they should be functions of k as well. So I will have a AK and AK dagger just like the definition we have used. So this is exact analog of the position in the operator language. So far so good. Now let us write down what is the pi corresponding to it, the conjugate momenta pi. From the new definition as we have seen, this is just phi dot times h square by c. Previously it was h square times phi dot because of our usage of del 0 phi as the conjugate variable to be traded off. But now we have just rescaled the c in, and then therefore I have this definition. So what should I do? I should take this phi which we have written upstairs here, and then I should write down its derivative. When I write down its derivative, the del t part will just hit this thing, and this phi k of t we have just written here. So ultimately you see the derivative of this with respect to time will just make derivative of this with respect to time, which will hit the exponentials. So exponentials will give me either minus iota omega and the exponential back, or plus iota omega with the exponential back, and there is overall 1 over c which is coming about. So that's what we have to do. So do it. Take the derivative of phi k actually, and phi k we have written over here like this. Just let me clean it up so that we can visualize very clearly. So what we have to do, we have to multiply h square by c with the time derivative of phi. Time derivative of phi involves time derivative of phi k, and phi k itself is known in terms of exponential I omega t and exponential minus I omega t. So the derivative operator will throw this and that. Okay, so this would be my definition of pi. There will be a relative sign difference, and there will be iotas coming from the exponentials derivatives. So overall, therefore, I have this structure. I have this structure that phi k, which I have here written like this, which is like before I have repeated, but then the definition of pi, if I want to write as Fourier transform of some pi k times e to the power ikx, this quantity here along with the factors which are coming about from here and here will be identified as pi k. So you just take this collection of this whole thing, this 1 by root 2 omega k and this root h upon h square kind of thing, then you will get pi k like this. This is just algebraic systematic way of writing the same thing. Okay. You can verify there is h square and root h factor coming from, because pi, remember, already came with h square factor, and phi k itself comes with a root h. So therefore overall h square root h will be coming out. So this is your phi k and this is your pi k. They are analogues of x and p. X was supposed to be summation of a to the power minus I omega t plus a to the power a dagger times e to the power I omega t. So p therefore is a 1 by iota a to the power e to minus omega t, a dagger times e to the power minus omega t minus a dagger e to the power plus I omega t. So this is what exactly x and p analog are mimicked by phi and its conjugate momenta in Fourier space pi. Okay, so neatly I can write the conjugate pair field and its momenta like this. I have just written it neatly over here in the boxed form. One more thing, we want our fields to be real. We are talking about real fields. Right now the discussion is focusing on real fields. There is no need to actually discuss real fields. Fields could be complex as well, because remember, initially we were after finding out the operator version of wave function, and there is no demand on the wave function that it has to be real. But for the special case, let us say, if we do consider special case that the field I am after is a real field, okay, it's a subset of all possible fields. Complex field could also be there, but I'm right now talking about only real scalar fields. In that sense, if phi is real, you can prove that its Fourier conjugate should be phi k dagger should be phi of minus k. This is not real. Its Fourier counterpart is not real. If phi x of t is equal to phi dagger or star, let us say, then it translates into the dagger of phi k is equal to phi of minus k. This you can prove from just a structure of phi. Just put a dagger to this equation and bring it back to its own form. You will realize that you have done this exact identification. If that is true, and you know phi k is this, so therefore its dagger should equal to phi replaced with a minus k. And that will give you conditions like this. A k should be equal to a of minus k, and a k dagger should be equal to a dagger of minus k. So that means these operators are symmetric undergoing from k to minus k. All these k's are vectors here. Okay, sometimes I write the vectors explicitly, but sometimes I have missed the notations of writing as a vector. So ultimately a of k vector should also be equal to a of minus k vector, and the same thing should be true for the dagger as well. So now let us get back to the Hamiltonian and try to see what does it look like in terms of these ladder operators or the creation and annihilation operators. We know at the classical level, when we wrote down, the Hamiltonian was made from quadratic terms. So there was a c h bar square by 2 outside. Then there was an integration d3x and pi square upon h4. So first let me uh, elaborate one more point over here. When we were writing this, remember this h was obtainable from the Lagrangian density. This was not full Lagrangian as we had discussed in the previous classes. This is rather Lagrangian density. So therefore, after the Legendre transformation, what I am getting here is Hamiltonian density, not the full Hamiltonian. Dimension wise, they should be the same thing. So this needs to be integrated over d3x to obtain the Lagrangian. Similarly, this Hamiltonian density needs to be integrated with respect to d3x in order to get the total Hamiltonian. So the same thing would be done. I just took the Hamiltonian density, which we obtained right now, absorbing the 1 over c square in the redefinition of pi as we discussed. Then the total Hamiltonian will be just integration of the Hamiltonian density over the space, over the volume. So this is my true Hamiltonian. Okay. Now here there are three pieces. One is this pi square upon h4. One is a gradient of phi square, and then there is a m square c square phi square. So we need to evaluate all these terms to know what the Hamiltonian looks like. This is a slightly elaborate mathematical procedure which I will just do systematically so that we become very careful. So just to appeal to the definitions, I need to know what is pi and I need to square it. I need to know what is the gradient of phi. I need to square it, and I need to know what is phi itself. I need to square that. So let us do bit by bit. First, I look for what is the pi. Pi we had just written in the boxed equation here. Pi is this quantity, h bar to the power phi by 2 iota by c, and then this integration of the quantity which is looking like a minus a dagger, the usual momentum in the harmonic oscillator kind of thing. Only thing is that the true pi is made from the collection of all such conjugate momenta pi k's, all together coming with the Fourier factor e to the power ikx generate for you the conjugate momenta pi. And I need to square this quantity. That means I will take this definition and multiply it with itself. So therefore, I would have a 1 pi coming with a single integral. Pi square will come with a 2 integrals. So there should be 2 integrals, which I have written as a symbol here. So actually it is something like this. d3k root 2 omega k. Outside, remember what was there? If you pay out attention, outside it was h to the power 5 by 2. After taking the square, it will become h. It would become h to the power 5. Okay, and there was iota outside as well, whose square should give you a -1, and there is a c square which should come in the denominator. So let me do it. So there should be a c square which I have put it over here, and there should be minus sign. We can keep it for the time being. Let us see, there is a minus sign over here. Then inside quantities will appear twice, once with a vector k and once with the vector k primed. So inside quantities where this omega k, ak e to the power minus I omega t, a dagger e to the power I omega t, and e to the power I k dot x. So which has appeared here, omega k e to the power I k dx, and this bracket which is appearing, and similar thing should appear for k primed as well. So all these quantities have appeared twice, and I have a pi square. So let me keep the minus sign everywhere which I apparently had not written down. So let me correct it. All right. Okay. Okay, fine. So, okay. So now let us see what do I get out of it. So remember, I need to do the d3x integral on pi square h4. So pi square h4 I can write from here directly. First I need to do d3x pi square integral, and then I can divide by h to the power 4. So when I do the d3x integral, d3x will search for the x dependency. X dependency is coming here and here only. There is no other x dependency anywhere. So I will get an integration like d3x e to the power I k dot x plus e to the power I k prime dot x. So together I can write it like this. And this I know is a definition of a delta function, three-dimensional delta function, which is vector k plus k primed. So this is what I have written over here. Okay, this should be fine. All right. And then there is a double integral which is left out, d3k and d3k prime. So this delta function ensures that all the k prime should take the value of minus k. Okay, and we know certain properties of things when they go to minus k. Ak goes to a of minus k, which is same as ak here. So k, this will go into a of minus k, but it is same as a of k as well. So but let us not use that. I just write as a of minus k. So all k prime would be written as a minus k. Omega k, remember, was supposed to be k square c square plus vector k square, this is magnitude, plus m square c4 upon h square. So when I take omega of minus k, this remains unchanged because it is square in k. The vector k magnitude and vector minus k magnitude are the same thing. So omega does not change. So therefore, instead of having omega k primed, it should have gotten converted into omega of vector k, omega of vector minus k, which is same thing as omega k squared. So which is what we have written over here. Okay. So overall, I would have a minus h5 upon 2. 2 will come from root 2 here, and root omega k prime, with identification that omega minus k is equal to omega k will give me just omega k downstairs. Upstairs I should have a omega k square upon c square, which is over here, and then all the operators where k is identified to be minus k dagger is identified to be minus k. So that is what I have written. So you can again should work it out to see exactly what we have written in the line over here should come about. Okay, so this is fine. Now let us look at one more thing. Since you remember there was a h bar to the power 4 here, h bar to the power 4 here, so I can divide it by h bar to the power 4. I do not know why I wrote a c square here. It should not have been, but it should have been h bar to the power 4. So that h bar to the power 4 will come in the denominator and will cancel the fifth power of h bar, and ultimately the first term will just be minus of h bar by 2 times the whole factor here. All right. Now let us go to the second factor. The second factor is the gradient of phi and then square it. I do the same thing when I look for a gradient. The gradient is with respect to positions. Vector x, it will search for position. It will only find positions in the exponential. When I take the gradient, it will bring down a iota k, the vector down. Taking the gradient of exponential ikx just gives back exponential ikx with iota times vector k back. And then I have to square it. That means I will write the integrals twice. So here, so with a k, here with the k primed, this is the gradient of phi. This is the gradient of phi again, meaning this is the gradient of phi k e to the power I kx integral, and the second thing is integration of phi k primed e to the power I k primed x. So these two brackets have come from the uh, multiplications of gradient of phi. Again, the same thing, I will undergo the integration in d3x. It will identify this pair of exponentials and convert it into delta of k plus k prime like before. The exact same thing. And therefore, the same game happens. One of the k primed is converted into minus k. So this time there is a subtlety. Previously, I had a omega k and omega k primed, and when k prime became minus k, it became omega k square, because these were the same thing. This time I have a iota k and iota k primed. First iota will give a minus sign, and then k and k primed is there, and with the delta function, when I do the d3 k primed integration, this k primed will be converted into minus k. So overall it will become into a plus k mod square. So you see, you will get a k square with a plus sign outside. So again, I will just suggest you to do this once carefully yourself, that you should take the gradient, multiply the two integrals, do the exponential integration d3x of this quantity. This will give you delta of k plus k primed, and use that delta of k plus k primed into one of the k primed integrals. You will get this result. Okay. Lastly, I have a phi square which I need to evaluate. So that means I have to just take twice of the same thing, phi, which was d3k of root h was outside, if you remember. Then there was a ak e to the power I omega t plus ak dagger e to the power minus I omega kt and e to the power I k dot x. And in the square, 2 times these quantities will come. So another root h bar will come, that will make h bar. Then there will be double integral d3k primed, another factor of the same thing repeated with e to the power I k primed dot x, and do the d3x integral to that as well, which is required here. And use again that there will be a delta function which you will get for k and k primed, You will get a delta function for k and k primed, and ultimately you will land up on this equation over here. Okay, so just let me clean things up once more so that we can have a quick look. What do we get from the pi square term? I'm going to get this here. This has to be divided by h to the power 4 as well to get the first term. From gradient of phi, I will get this term over here. And from the mass term, I would get this term here, which needs to be multiplied with m square c square h square. So m square c square h square. So if I combine this quantity and this quantity here, m square c square h square, you will see all those quantities are appearing like they are appearing here as well. So they will just add up. So k square will add up with this. H bar is common outside, integral is common, and the whole factor is common. So from the last two terms, you will get the same kind of integrals with k square plus m square c square upon h square times the integral d3k and the whole object here. Now look at the term over here, which is coming from the first term. It also has roughly the similar kind of structure, but you see there is a sign difference. All the terms appearing here are positive. Here some terms are negative, and outside there is a negative factor. So these terms will become plus sign, the upper terms will become minus sign after you absorb the minus inside, and they will exactly cancel these terms. These terms here, here, here are exactly cancelled by these terms. So all you are left with time independent terms. So if you just do the algebra carefully, you will be left with time independent terms only, and you would get the answer that these things will combine. When this was the here, the minus sign will become plus, all these quantities are plus. So ultimately there is omega k square by c square. The factor coming from the last two term is also this k square plus m square c square upon h square, which is also omega k square by c square, by the way. So you will get twice of omega k square upon c square, but there is a 1 over omega k outside as well. So ultimately you will get omega k here and not omega k square upon c square. So omega k upon c square. So only these terms will survive. So you see, now the whole algebra has, using the ladder operators, have given me a neat structure of Hamiltonian, which is made from just A and A daggers, just like a harmonic oscillator does, right? Only thing which you have is that here I have a minus k and here also you have a minus k, but this should not worry us because we already know that a of minus k is equal to a of k, and a of minus k dagger is also equal to a of k dagger. So ultimately this is indeed very much like harmonic oscillator plus ak dagger. So this is what we get for ordinary harmonic oscillators as well. In position, if you in position space, if I write down the Hamiltonian of an ordinary oscillator for a single oscillator, exactly this structure comes about, that you will get a h bar omega times this. Now here you are getting an extra factor of 1 over c square and these quantities over here. We do not have to worry about it, as we will see that they will just reabsorbed in the redefinitions of this. But one last stage was, harmonic oscillator in quantum mechanics can be written, their Hamiltonian can be written as number operators plus half and h bar omega. We are almost there. So we are two steps away. One is that proving that these things are number operators, and second thing, absorbing these extra constants which are appearing. So let us go in stepwise. First, I would want to prove that this has a number operator structure. In order to have this number operator structure, we need to know what is the commutator between AK and AK dagger. We have never specified, we just wrote down AK and AK dagger, converted them into operators, but we do not know what their commutator is. In ordinary harmonic oscillator, A and A dagger are supposed to satisfy commutator relation identity. So if similar kind of thing exists here as well, then we know Even the Hamiltonian becomes exactly like harmonic oscillator Hamiltonian for each k, and then it is just collection of oscillators. Their energy is constituting the total energy of the field as well. Okay, so that we will do the rescaling and getting the commutator relations between the ladder operators we will do in the next class. So I stop over here.